So let's summarize. We just learned about polyprotic acids. We learned that polyprotic acids are the acids that actually exist predominantly in nature. They're pretty much all of our biomolecules, which have, in the larger biomolecules like proteins or pieces of DNA, literally millions of acid sites, literally millions of places where a proton can come on and go off. That means they have literally millions of pK values associated with them. So if we're going to work with those kinds of chemical systems, we really need to understand some of the tools that make it possible for us to do that work. One of the simplest tools is to hope that we're working with systems in which the K values are far apart, because if that's true, then I can develop strategies based upon the monoprotic acid-based systems that we've looked at, knowing that the only new information I need is the ability to do an amphiprotic case where I have a polyprotic acid. More commonly, though, because I have a relatively narrow pH range, typically between 0 and 14, if I start putting 3, 4, 5 proton regions, protonated regions within that 0 to 14 range, it's going to be impossible to get 3 or 4 orders of magnitude separation between my K values, which means it's impossible for me to apply most of the time these simple monoprotic acid-base case examples. What I have to do then is to remember that lecture on complex equilibria and understand that there are mathematical tools for treating the situation where if you know the number of unknowns, you can create an equivalent number of equations based upon mass and charge balances and chemical equilibria and solve the cases that way. And that is, in fact, how people typically work with these kinds of systems.